Hello everyone and welcome back to a repair video. At least I will try to repair this board. I don't even know what's wrong with it. I only know that it is not supposed to work. So we'll figure this out today. I have no idea what board this is. There is no model number printed anywhere on this board, but it looks like the PCI slots are numbered 0, 1, 2 and 3. And the ISA slots are not. Then we have a very limited table here on the side how to configure two CPUs. One is a DX4 and the other one is the Pentium Overdrive. I'm sure there are a lot more options in the manual, but anyway, this seems to be a very interesting board. First of all, well, it has PCI and ISA slots. That's interesting. It also has VLB, VESA Local Bus slots, 2 of them, but I have no idea what chipset this is. So, Then we have level 2 cache, which has write back written on it. That's already suspicious, I think. I'm not sure. I just had bad experience with level 2 cache that tried too hard to be level 2 cache, and in the end it wasn't anything. So yeah, 486 board, quite modern I would say. Let's first figure out what board this is. The RetroWeb is a really good resource trying to figure out what board you have if you don't have a model number printed on the PCB. So what I did is I just used the advanced search for motherboards. I entered a socket 3 board. We have 4 PCI slots, 4 16-bit ISA slots, and 2 VLB slots. And we only get a total of 14 boards. So we should be able to figure out quite quickly if our board is in the search results. And I'm looking for pictures that have all black plastic slots, but looks like none of them have. Now we need to look a little bit at the layout of the board. This looks very similar. The PCChips M915i. And we get a few pictures here, but none of them have all black slots. That's interesting. The one that I have here has all black slots, even the VLB and the PCI and the ISA slots. Oh, okay, this was a board that was also available under different names. Uh-oh. No, really? Labeled as right. Oh, I knew it. I really didn't look this up, but I just had such a bad feeling about these cache chips. And what's really bad is that these are soldered to the board. Okay, and apparently we can set the amount of cache that's on the board, which we can look at later. Let's first figure out if this is actually fake cache or not. So, 10 minutes later, and looking through all this chomper mess that you can see here, on this board was an Intel DX4 100. This is what I could understand from the chompers, how they're configured right now at this moment. Also, the voltage is set to 3.3 volts. So yeah, it makes sense that there was a DX4 from Intel in it. So I want to change the configuration to an AMD 486 DX2. Let's quickly check for shorts. So the center pins here are all ground. And here's 5 volts. No, there is no short here. I think then we have ground. Yeah, ground, 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 ground. Let's see if any of these pins are shorted. This is still ground. No. Okay, there are no shorts on this board. Let's plug in the power. First thing, let's measure if we get 3.3 volts on our socket. I already figured out that this is our voltage regulator for the CPU socket. I basically just checked one of these pins that supplies the CPU with power, and it connects to this pin that is on the far left. So let's power on the board and see what we get. First time powering on, and okay, nothing exploded. That's good. And we get 3.5 volts. That's okay. Our CPUs get the correct voltage, but I want to check now the 5 volts. That will most likely disable our voltage regulator and take the power directly from the power supply, the 5 volt rail basically. So 5 volts definitely coming in here. I'm not sure if they're on that voltage regulator. Voltage regulator still delivers 3.5 volts. So most likely these chompers disconnected the voltage regulator from the CPU socket. The RetroWeb also has the specification for socket 3, and if we look here, then we can see that VCC is right next to our key pin. I'm just using the resistor to poke the socket, that's it. So we get 5 volts, we get 3.3 volts. The entire setup changed again because, well, my AMD DX266 are not easily accessible right now, but I found this DX2 from Intel. Now we have to make sure that we line up the dot or the cut corner with our key pin or where the lever is. This usually is where pin 1 is. So we need to make sure that all of this is correctly lined up. Then we need FPM memory. 1 stick should be enough. This is a 32-bit data bus, not like the Pentium. Pentiums have 64-bit, 486 has 32-bit. And I put everything together. So here's our postcard. CPU is in the system. Let's see if we get postcodes. Oh. Well, we do. I think this board is working. Maybe the owner of this board used EDO memory instead of FPM. So that is always an issue. If you're using a board like this with EDO, it may not boot. So here is a 32 megabyte EDO memory module. Let's see if we get different postcodes. And you see, sorry for not having a sharp image here, but it's looping. So yeah, you need FPM memory. Let's try one more time with the FPM memory module. And there we go. Okay, very interesting. I didn't see this before, but this board doesn't have any onboard floppy controller. It only has 2 IDE ports. So this is my recently fixed S3 Trio 64V Plus, and we have an AMI BIOS, exactly as I thought. Okay, so 32 megabytes is detected. We have CMOS is empty because, well, there was no battery in it. And okay, let's try F1. Hey, ooh. Ah, this is one of these graphical BIOSes. I have never had one of these. Interesting. Of course, we want to figure out what's going on with these cache chips. So I think I will continue and you should continue watching. L2 cache is right back. Let's see what we get in NSSI. I don't see any mention of cache. So let's see. Second level cache not available. Huh. Well, at least the board is working, so this is already a good sign, but it looks like that there is an issue with the cache. And if that is the case, well, maybe instead of a repair, we are swapping out these cache chips for real ones and see if it makes a difference. How about that? There will be a drop after 8 kilobytes. Now, yes, so this is the CPU. Now let's see what happens after 256. This is the big question. So this is how it looks like when you have cache in the system. The 8 kilobytes are on the CPU die. Do we drop? Okay, so we have fake cache chips on that board. And most likely, the BIOS is patched to always show 256 kilobytes of level 2 cache, even though there is none. So yeah, now I think it's time to get out the desoldering station and get all these chips removed from the board. The BIOS chip, as well as the fake cache chips. We have again fake cache. I can't believe it. These cache chips are melting. This is just regular plastic. There is absolutely nothing in them, 100%. It also starts smelling. Burnt plastic. Okay, let's try to get them out from this side. Okay, I think that works somehow. What a mess. It doesn't even have a proper body. It is just a plastic case. Oh my goodness. Yeah, no wonder they are not socketed. They are soldered to the board directly. What a scam. If you're interested in a hot air station like this, you can find links on my website where you can buy this. And I think this went really well, but I can't believe that these chips look like that. Look at that. There was a factory that produced this garbage. But it looks like there are traces going. It looks like they're connecting to either this chip or this chip. It's definitely not the very obvious fake that is visible on some other boards. I have a board like this. There are just two cache locations where traces connect to each other and nowhere else. So this one here is the real-time clock. I want to remove this one and the BIOS chip as well. I want to dump the BIOS to see if I can spot where they hacked the BIOS to always show 256 kilobytes. So I did not expect this project to go this direction at all. First I thought maybe there is a fault on the motherboard somewhere, but then it turned out it was only the memory that was not compatible, most likely. And then suddenly we ended up with fake cache chips. I'll not bore you with cleaning up this section because it's very repetitive. So I'll do this, then I will install the sockets, and then we'll try the board. See if we still get 256 kilobytes of cache. And the sockets are on the board. Now we have the sockets for our L2 cache, and we have our real-time clock as well as the BIOS. So let's install our BIOS chip because we want to see now if we still get 256 kilobytes of level 2 cache. And we need our real-time clock, but the cache chips remain empty now. I just want to see if the BIOS still reports 256 kilobytes of level 2 cache. I'll do this off camera. Okay, let's see if the board survived. Let's power on and...
No postcodes.
Nothing. Okay, I destroyed the board, unfortunately. Why? Well, I added the sockets and followed the silk screen, and you can see it here. This is indicator that here is supposed to be pin 1, but if you look at my initial footage when I showed this board, I really should have checked. The real-time clock chip is supposed to go in like this. So it's not lining up with pin 1. It destroyed the real-time clock chip, and most of these pins go into the chipset. I'm not sure if the BIOS chip is going to work. I wanted to know which model number this is, and yeah. So I have no idea. I really do not like PCChips boards. I do not have a sponsor for today's video, but I would like to remind you that the ALL64 memory expansion boards are ready. If you're interested in one of them, you can head over to PCBWay and order your PCBs. You have to assemble it yourself. However, if you would like to, you can reach out to me and you can buy one of these boards fully assembled. I already made videos about the MIDI Forge Sonata, which is a 28 megabyte expansion board, and the MIDI Forge Minuet, which is an 8 megabyte expansion board for your Sound Blaster AW64. However, the MIDI Forge Rhapsody is also finished, and I have this board in two versions. This is the white one, but I will also have the matte black with yellow silkscreen. So if you want one of these boards, check the video description. There are links to my website. Each board has its own article, and you will get links to PCBWay's shared project space. So what do we do with this motherboard now? Initially, I thought I make a two-part video, but nobody likes that, and I want to also finish this project. That's why I give you now a little bit of a summary what I have tried and to which conclusion I got. So I was pretty much convinced that this chip is fried because this was upside down in the socket, and that is the original chip, easily identifiable by the R in the top right corner. I used another chip, this is also real-time clock, same model number from another motherboard, and well, I tried to put this chip like this into the board, run the motherboard, but there was no change, still no postcodes. Then I went ahead and I replaced this chip. Now, based on the RetroWeb, this is a UMC chipset. This is the UMC 8886 and this is the UMC 8881. I guess the 6 and the 1 will give it away which chip is which. Somehow I have 5 of the 8886 chips for whatever reason. I don't know, I guess it's for this. And yeah, I went ahead and replaced the chip, and I could show you 10 minutes of desoldering and soldering. But yeah, I don't want to waste your time with things that are not really relevant to this entire project. I can tell you that after replacing the chipset, it did show a normal heat signature, what I would expect from a working chipset. So I believe that this is a UMC 8886. But yeah, even that didn't fix the problem with this board. Now, the next step would be to replace the UMC 8881. However, I do not have a replacement and I do not want to take it from one of my working boards or even from boards that I haven't tested yet. So that left me only with these two clock chips, and I did notice something. If I insert the replacement real-time clock chip like the original was in that board, the reset line gets stuck. That does not happen when the original chip is back on the board, obviously like this, in this orientation. And that got me thinking. So I checked the datasheets of one of these real-time clock chips. It's very difficult to find, and I couldn't find a datasheet for this exact chip. But apparently this real-time clock chip was also manufactured under different model numbers. And I used one that made sense. And what it said is that the second and the third pin are clock inputs, and one of these pins goes to the 32 kilohertz crystal that you see here. So I tried to figure out if this chip is really burned, and I could do this by comparing the resistance between different pins and see if there's a pattern and match it to this chip. Okay, I have my multimeter in resistance mode. I think this is the easiest one for everybody to understand, including me. Now let's just measure from pin to pin. So I'm taking one probe to the very left, and then we'll just measure the resistance between those pins. So we have 13, then we have another 13, 13, 13, 13 mega ohms. This one here is open circuit or open line. 13, open line. 13, open line. And 8 mega ohms. So this is on the original chip. Now let me measure the other one, the replacement chip. I know this one is working because I tested this one in another system. So let's see what readings we get from this chip. Okay, 13, almost 14, but there are some manufacturing differences. Next one, open line. Okay, that's different from what we had before. Okay, next one, open line. No connection. We got always 13 mega ohms. Okay, so there is no reading on any of these pins. Then I thought, okay, let me try the other way around. So let's see what we get here. 14 mega ohms, exactly like the other pin. Next one, 14 mega ohms. Next one, 14 mega ohms. Then 14 mega ohms. Then 14 mega ohms. Open line. 13 mega ohms, I think. Yes. So this one is just at 14. Then we have open line. So, that doesn't make any sense. So the pattern on this side, where it's indicated for pin 1, behaves exactly like this row of pins, which is opposite of pin 1. So could it be that this real-time clock chip is flipped? Is this R indicating that the pinout is reversed? Pin 1 is actually here where the R is? This is what I believe now after measuring these pins in reference to always the left outer pin. Just to double check, let's measure the outer left pin with the outer right pin. This gave us our 8 mega ohms. So let's try this on this chip now. So the very left and the very right. Open line. Let me turn this around and let's see what we get now. 8 mega ohms. This is the chip that has the correct pinout. This is the replacement chip. This is the chip that was on the board with the R. The 8 ohms are on this side. On the other side, we probably will get open line. Open line. So yeah, I think this chip still works, but it is reversed. Pin 1 is here where the R is. It does bring up the suspicion that PCChips tried everything possible to make sure people will not understand what's going on with their boards. You saw their BIOS chip. It just has the big letter D lasered on the surface and then covered with a sticker. And even the chipset doesn't give you a proper model number. Well, and then to top it off, you have the entire fake cache issue. So yeah, it really looks like this is deliberate. But if you know more information, I'm really curious. Write it in the comments and let me know what you think about my findings that these real-time clock chips have the same model number, but the pin layout is reversed. Okay, moment of truth. I put now another real-time clock in there. This was the old one, but this one was in there like this. So let's try what's going to happen now. Ready? No. So the silk screen is correct. This is a reversed clock chip with the same model number and an R in the corner. Yeah, it works again. Okay, well, now we can continue with the rest of the video. It didn't even occur to me to test the original real-time clock chip after I realized that I placed it the wrong way in the socket and powered on the system. So, as I said before, I believe this real-time clock chip still works. Let's find out. And it boots! Wow. What a mess. Okay, so no cache on the board, will we see 256 kilobytes? And yes, 256 kilobytes cache is still shown. So yeah, we have again a patched BIOS. This time it's an AMI BIOS or American Megatrends. Unfortunately, I couldn't yet dig into the BIOS. I was able to get a copy of it, at least I believe so, but it was not easy to get a backup of the BIOS. Several programs, including UniFlash and a tool that was used to flash AMI BIOSes, did not work. As it turns out, another interesting fact about this board, it uses a one-time programmable BIOS chip. So yeah, you cannot update your BIOS. This board came with a BIOS and that's it. But it looks like this BIOS is somehow compressed and I would have to decompress it first. I didn't have enough time to look into this yet. So yeah, I couldn't really figure out how they patched the BIOS yet. If you know how to decompress this AMI BIOS, you could try your skills. I will create a very small blog post where I will offer the files for download and you can go nuts with it. I will have the link in the video description. Let's crack this together maybe. And if you're looking for a challenge, maybe this is something you would like to do. Okay, let's hope there are no more surprises with reversed pinouts. I tried 3 different sets of cache chips and I verified the configuration on the board. Here is the configuration for the M919, but I altered it to reflect the correct configuration for the M915i, the one that I have here. And the configuration is correct for 256 kilobytes of level 2 cache. And this is what I installed on the board right now. So it still doesn't work. The only thing I can think of is that the BIOS was patched in a way that it doesn't work with cache at all. The problem I have right now is that I don't know which BIOS chip I can use instead of the original one. If you know, please let me know in the comments. I will not continue right now trying to fix this as well because I think the video is long enough. If you do want to crack the code behind the BIOS and how they patched it, please be my guest. I will link the post to my website in the video description. And I think with this, we should conclude this video. I also want to thank all my Patreons that are already supporting my work. If you want to support my work, then you can head over to Patreon and pick one of the paid membership tiers. Otherwise, you can just leave me a like on this video and subscribe if you haven't already done so. Thank you so much for your time, thanks for watching, and I will see you in the next video. Take care and bye-bye.